Hello everyone, today we're building a stunning ocean diorama. This project features a fully functional lighthouse with real lenses and a rotating beam, along with beautifully detailed environmental elements. At its core is a sophisticated algorithm that generates realistic shoreline waves designed to feel natural and organic, with varying intensity, duration, and random intervals. The system includes 7 distinct wave patterns that occur with random probability, ranging from calm, glassy water to dramatic storm conditions, complete with LED flickering and immersive visual effects. I put a lot of effort into every one of these videos, so if you enjoyed it, please like and subscribe. Thank you. To kick off the build, I designed all the components in my 3D modeling software and brought them to life using 3D printing. This part is the lens holder, which powers the rotating beam. I repurposed lenses from small keychain magnifiers, carefully bonding them into place for custom lens setup. For the light source, I'm using a powerful 12-volt automotive LED. To keep things cool and achieve a more comfortable brightness, I'll be running it at 9 volts instead. And this is where the LED will be mounted after I solder a couple of wires to it first. You'll need to make sure that the LED is hanging down completely straight before fixing it in place with some glue. Since there isn't enough space for a motor in the lighthouse base, I used a pulley system to transfer motion from a horizontal drive outside the lighthouse to a vertical rotating mechanism. I built a compact transmission setup using a couple of gears and shafts salvaged from small DC motors, using plenty of grease to make sure it rotates smoothly. After gluing the transmission assembly beneath the lighthouse cage, I mounted the lens setup onto the main shaft. The entire mechanism should now rotate smoothly and freely when the pulley is turned. Next, I closed the lens chamber. After routing the LED wires through one of the cage supports, I bonded the LED bracket to the assembly. The lens chamber now rotates smoothly around the stationary LED. This is the lighthouse cap. I drilled 2 holes so I can mount an LDR light sensor on top. Then routed the LDR wires down through the same opening. To save yourself some hassle, loop the string belt around the pulley before mounting the lighthouse head onto the base. You might be wondering why am I using a string instead of rubber belt. Rubber can build up tension, then release it as a burst, which makes the rotation jerky instead of smooth. Here's the full glass enclosure. To keep the video concise, I included a clear diagram showing exactly how you can build it yourself. Route the LED and LDR wires along with the string belt through the hole in the top glass panel. It's crucial to properly seal the lighthouse base to prevent any water leaks. To rotate the lighthouse beam, I'm using a low RPM DC gear motor. Mine is a 4 RPM model rated for around 9 volts, but I'm underpowering it to make it operate smoothly and quietly. After mounting the motor to the base glass panel, apply just enough tension to the string belt to keep it engaged. Then add a small drop of glue to secure the knot and trim off the excess string. The string belt should now start rotating along with the pulley, though if it starts slipping, you can fix it by simply increasing the tension until it grips properly. Now draw a line to mark where the shoreline meets the raised ground. I 3D printed these structures to act as anchors, helping the concrete adhere to the glass enclosure. Concrete doesn't directly bond well with glass, so these provide crucial grip. I also made these light poles, built from 2 3D printed tubes, an LED holder, and a pair of thin wires. To generate the waves, I'm using a quiet brushless pump paired with a custom 3D printed nozzle to direct the flow just below the water surface to make the waves. After mounting the pump to the glass panel, route its wires through the gap between the glass panels and seal everything securely with silicone sealant. Also wire the light poles in parallel and route their wires down through the lighthouse. I used gravel and black concrete to form the raised ground area. This step is fairly straightforward, but remember to add another pair of wires and route them down through the lighthouse. I'll show you what they're used for later. I temporarily seal the back area with tape so concrete doesn't drip down. Once the concrete has fully set, glue clean gravel over any dark or stained areas to give the ground a more natural and polished look. I then drew a pathway over the concrete, running it beneath the light poles so the path would be naturally illuminated by their glow. I used this grass material, mixing both colors to create natural looking variations across the ground. Once the grass material is poured over the glue-coated surface, press it down by hand to ensure it adheres properly and stays in place. After that, use a vacuum cleaner to remove any loose or excess fibers that didn't stick to the glue. To create the ocean floor, I'm using 4 different shades of sand to add depth and realism to the seabed. Spread glue over the glass panels, pour the sand on top, and press it down by hand so it sticks firmly to the surface. Now to create the color gradients, fill the narrow area between each color transition with a mix of the 2 neighboring sands. Make sure the blend shifts gradually. More of the top color toward the top and more of the bottom color toward the bottom, so the transition looks natural and smooth. Now simply repeat these steps all the way down. I used 2 pieces of paper to map out the exact angle of the sea's slope so I could cut the dock columns accurately. After taping the papers together, I used a template to mark precisely where each column needed to be cut. You need a pair of each. I also cut many smaller sticks to serve as the dock's flooring, attaching them directly to this 3D printed support bar. To add a nice warm glow underneath the dock, I used a small LED string securing it in place with 3D printed hooks. I got this little wooden boat and added a tiny LED that make it glow nicely in the dark. The boat's LED is soldered in parallel to the wires powering the light poles, while the dock's LED string is connected to the separate pair of wires we installed earlier. Use plenty of silicone to seal all the solder joints. If moisture gets in, they'll corrode and eventually stop working. Scrape away the sand and install the dock columns, making sure their tops are perfectly level with each other. Attach the dock floor to the installed columns, then proceed to install the remaining side columns to complete the structure. Fill the gap with more silicone, then apply a concrete finish on top to conceal it. Now anchor the boat to the dock using a piece of manila rope or simply use the LED wires for a cleaner, more discreet look. Now apply a very thin brown acrylic wash over the wood to give it a weathered, more natural look. The diluted paint settles into the grooves and textures, adding depth and realism. To create a realistic tree, take multiple strands of manila rope, twist them together at the base, and secure them with superglue. Shape the loose ends into branches and harden them with more superglue. Finally, trim the branches to your liking and apply the same grass material we used earlier to give them a natural, leafy texture. I found these decorative dried plants online and I'm going to attach them to the rocks to give the scene a more natural and detailed look. This is the entire control board. It's built around an Arduino Nano along with a MOSFET driver and power MOSFET to control the pump, plus a couple of transistors to manage the LEDs. Here's the complete circuit diagram and the rendered PCB layout ready for printing. For my first attempt, I programmed the Arduino to simply pulse the pump on and off for random durations at random intervals. But this turned out to be a mistake, as you'll see later. For now, let's continue with the rest of the build. After soldering all the connections to the control board and adding a DC power jack, I glued it to the bottom panel. I used one of those readily available 5V touch switch modules to turn the unit on and off. To prevent random shutdowns, I added a small capacitor across the module's power input. After installing the water nozzle, I wrapped the entire glass housing with a matte black wrap, covering all the bottom components and any visible glue traces. While applying the wrap, I accidentally broke the duck, so I had to rebuild it. That's why it looks a little different now. Now I'm adding dark green acrylic stains around the base of the duck columns, then softening them with a wet brush to wash the color out. This creates a realistic algae buildup effect. Now I'm adding small blobs of glue at random points near the shoreline, right where the water will be. Then I'm placing some of those dried resin-treated decorative plants into the glue to create a natural seaweed effect. Now turning it on for the very first time, and it is not quite what I expected. The pump just pulses on and off, and the water jet is too concentrated in the center, creating uneven waves. I'm going to fix all of these issues next. To start, I designed and 3D printed a full width nozzle so the pump transfers energy across the entire water surface instead of concentrating it only at the center. I then removed the old nozzle and installed a new one in its place. After attaching the pump's hose and running it for the very first time, this looks much more promising than before. I then add an LC filter to smooth the signal and unlock full PWM speed control over my BLDC pump. I also updated the algorithm. The new one constantly changes wave energy, rhythm, and intensity using layered random physics models, memory-based wave behavior, adaptive storm phases, and continuous micro ripples. So the water never truly repeats or goes completely still, just like a real sea. And this is much more like it now. The sea now dynamically shifts between calm seas, rolling surf, rough chop, and rare storms. Each mode changes the wave strength, rhythm, and density in real time, while adaptive micro ripples keep the water constantly alive and natural. Storms are rare, dynamic events that slowly build from normal wave conditions into dense, chaotic, high-energy water movement before gradually calming again. During storms, the LED is synchronized with the wave energy, producing soft, reactive flashes and brightness surges that mimic distant lighting and turbulent seas without harsh flickering. Thanks to the LDR sensor, the lights automatically turn on when it gets dark. If you want any of the files of this project or want the Arduino sketch, let me know in the comments. And once again, I put a lot of time and energy into every one of these projects, so a like, share and subscribe would be greatly appreciated. I would also love to hear your thoughts and any suggestions for future projects, and I'll see you in the next video.